Hello, and welcome to the video lecture for topic 17, the E1 reaction. Also, this is our last video lecture before fall break. Woohoo! Alright, so elimination reactions proceed by the loss of a leaving group and removal of a proton from a suitable electrophilic starting material to produce a new pi bond in that electrophile. Right? So the first elimination reaction, or the first elimination mechanism we're going to look at in Chem 201, right, is the E1 mechanism. When we get back from fall break, we're going to take a look at the E2 mechanism. So, as we have seen with substitution reactions, right, the name actually tells us a great deal about what's going on in the mechanism. So let's just start off with, what does the name E1 tell us? Well, the E tells us that this is going to be an elimination, which typically makes a new pi bond. And the 1 tells us that this is a unimolecular reaction. And we remember from our discussions on SN1 chemistry that when we say a reaction is unimolecular, it means that the rate determining step only involves one species, right? And that should also indicate to you that, similar to a SN1 type reaction, in an E1 reaction, a carbocation will form. So we know, or we have an indication that a carbocation will form. All right. So if we know a carbocation is likely to form or will form in a reaction mechanism, we need to be on the lookout for a couple of things. We need to watch out for carbocation rearrangements, and we need to be looking out for SN1 side reactions. Finally, the formation of a carbocation during an E1 elimination, right? We know that only an electrophiles that can form a carbocation are going to participate in these type reactions, right? So we know that this means we're going to have something that's either benzylic with a leaving group, right? Or allylic with a leaving group, or tertiary with a leaving group, or secondary with a leaving group, right? Because a carbocation forms in an E1 reaction, we know that these are the only types of substrates, the only types of electrophiles that we can have participate in the E1 reaction. So now that we've kind of taken a look at what do we need to know about our starting electrophile, what are some of the properties of the mechanism and the pathway that this elimination is going to occur down, right? We need to take a look at what are the different products that we can potentially form and kind of get a sense of what we should be on the lookout in determining which products are going to be major or minor products in our reaction. And so we've said that this E1 reaction typically makes a new pi bond, or actually not typically, but always makes a new pi bond. And we're going to see that this most frequently results in the formation of an alkene, right? Regardless of what type of leaving group I have, right, I'm generally going to form an alkene as my product. And so now we want to compare the stabilities of different alkenes. So we're going to look at 4 different scenarios. We can have what's called a monosubstituted alkene, where I have 3 hydrogens off of it. We can have a disubstituted alkene, and there's 2 types there. I can either have 2 R groups on 1 carbon, or 1 R group on each carbon. I can have a trisubstituted alkene that has 3 R groups overall. or I can have a tetrasubstituted alkene, a fully substituted alkene. Each carbon of that alkene has 2 R groups on it. So we have mono, we have di, we have tri, and we have tetra. Now, what I'm going to let you know, and you can verify this both in the POGIL worksheet and in your reading in Sorrel, is that the more substituents we have on an alkene, the more stable it is. We have empirical experimental data that proves this through the energy required to reduce these different types of double bonds, a mono-substituted versus di-substituted versus tri-substituted versus tetra-substituted double bond. But all of this empirical data, right, and all of the theoretical data and theoretical calculations that we can do all confirm that mono-substituted is the least stable, di is a little bit more stable, tri is a little bit more stable, and finally tetra is the most stable. Okay, so now we can say, so now this is talking about our electrophiles, what we have here, and now for our products, we can say that the order of preference that we have for products, because similar to our order of preference for electrophiles, right, this trend follows carbocation stability. We're going to talk about stability from most stable to least stable in terms of our products, right? Our tetrasubstituted alkene, right, is going to be more stable than a tri-substituted alkene, which is going to be more stable than a di-substituted alkene, which is more stable than a mono-substituted alkene. Right? We don't consider unsubstituted alkenes because that would have to come from some sort of electrophile that the leaving group is on a primary carbon. E1, you can't have that happen, right? We can't form a primary carbocation, so we can rule those out. We don't need to worry about those in considering our products. Now, the last thing we need to worry about in our products is EZ cis-trans isomerism. And for steric reasons, right, and you can again read about this more in detail in Sorrel, for steric reasons, an E-alkene is more stable than a Z-alkene. Similarly, a trans-alkene is going to be more stable than a cis-alkene. So now we know some of the properties of our mechanism. We've used those properties of our mechanism to give ourselves some things to watch out for: carbocation rearrangements, SN1 side reactions, right? This informs, knowing that we have a carbocation, informs us as to preference of our electrophilic starting material, right? Kind of what order that's going to go through. And then finally, right, knowing about stability of potential products allows us to know what we're looking for in terms of the final products that come out of this reaction. By the way, this trend here that E1 reactions prefer to form tetrasubstituted alkenes over tri or di or mono, this whole concept that we have in products is known as Zaitsev's rule. Zaitsev was a Russian chemist long time ago, right, who noticed this trend characterizing the products that resulted from E1 type eliminations and found that these trends tend to hold true. So we know that the distribution of our products, or the preference of formation of our products, we call that Zaitsev's rule. In E2, we're going to see a different type of product and a different rule that's going to play a role there as well, but we'll save that for after fall break. All right. So now that we have some basic groundwork here about the E1 reaction, let's go ahead and move on to take a look at the 3 possible scenarios that we're going to encounter, right, when we're doing E1 chemistry. So with the information that we covered in the first part of this video lecture, we're now ready to move on and begin looking at the different types of electrophiles that we're going to encounter in E1 reaction. And the 3 that we're really going to take a look at are alcohols, sulfonate esters, and alkyl halides. So we're going to begin with E1 reactions of alcohols. So this is going to be for our ROH. Now, Similar with SN1 reactions of secondary, tertiary alcohols, the first step in an E1 reaction is for us to protonate that alcohol. So now I'm going to draw here a tertiary alcohol. And I'm only going to explicitly draw out the hydrogens on one of my other carbons. And so here, similar to an SN1 reaction, I'm going to need to activate, right, or activate this alcohol, or another way I can say that is convert that OH into a good leaving group. And so the first step is to protonate it. Now, there are lots of different acids you can use to protonate that alcohol, but the best acid to use for an E1 reaction with alcohols, right, is going to be sulfuric acid. And we're going to see why that is here in just a moment. Now, I'm going to skip a lot of my lone pairs, but remember that whenever you push arrows, whenever you draw a reaction mechanism, for me in Chem 201, you're going to be expected to draw full Lewis structures that include all lone pairs. And so first step, we're going to go ahead and we're going to have this oxygen get protonated from H2SO, or alcohol oxygen is protonated from H2SO4. Sorry, here my pens are starting to run out of ink, and so keep hopping around looking for a good one. All right, so that's our first step, right? That gets us now to our oxonium. And the reason sulfuric acid is a nice choice for us to protonate our alcohol with is because its conjugate base is both a weak base and a poor nucleophile. So once I form this carbocation, right, I don't have to worry about sulfuric acid or the conjugate base of sulfuric acid acting as a nucleophile. So I reduce the potential for an SN1 side product to be formed. So here now, in my second step, my leaving group falls off, and I generate my carbocation. Again, I'm going to draw out one of my hydrogen atoms, one of my methyl groups explicitly with its hydrogen atoms. Right, the carbocation intermediates, we put those into brackets because they are short-lived intermediates. Now, I've formed water, which is a weak base, and I've also formed, right, I still have my conjugate base of sulfuric acid from my first step, which is also a weak base. Now, to determine which of these two, right, so remember we said E1, we first have a leaving group, at some point we need a leaving group to fall off. We also, right, so that's got to happen first to form a carbocation. After that, we're going to need to remove a proton. So I now have two weak bases that can potentially remove this proton. And I have to just be able to decide which of these two I'm going to use in my last step. And to do that, I want to look at what is the pKa of the conjugate acids of these two potential bases. Well, the conjugate acid for water, H3O+, has a pKa of -2. The conjugate acid of sulfuric acid, of this weak base, right? It's going to take me back to sulfuric acid, H2SO4, and sulfuric acid has a pKa of -9. I always want my acid-base equilibria to form the weaker acid, which means out of my two potential choices, the weaker acid will be H3O+, which means H2O is going to end up being the stronger base out of these two. And so the oxygen of water will deprotonate and give me my final product, my alkene. So here now is my alkene. I have formed a di-substituted alkene, and I have regenerated, right, one molecule of acid. This time my acid is H3O+, but it has balanced out that positive charge by sulfuric acid's conjugate base, right, which showed up for us after our first step. And so here now, right, why did I pick tert-butyl alcohol? Well, I can't do a carbocation rearrangement to get a more stable carbocation, and no matter which methyl group I remove a hydrogen from, I will always end up with a single product. This is a very simple example used in order to conserve time in the video lecture. Your POGIL worksheet does a really great job, and I really advise you to take your time with looking at it and going through all of the possible ways that very, very different alcohols, even different tertiary alcohols, can potentially do eliminations and generate a wide range of products. In fact, I'm pretty sure that there's one example in the POGIL worksheet where a single alcohol can form up to 5 different products, right? I think there's something like 3 different protons that you can remove, right? And you get different degrees of substitution on the alkene, and you have potential for easy isomers in all of those as well. So this is where I'm going to leave off our discussion of alcohols in E1 reactions, except to say one last thing, that when we do an elimination, right, when we do an E1 elimination on an alcohol, you'll notice that overall from the molecule, we are removing 2 hydrogen atoms and 1 oxygen atom. And so we are removing a molecule of water. And so formally, we can also describe this reaction as being a dehydration of an alcohol, right? So you'll often hear, right, when alcohols undergo secondary, tertiary benzylic and allylic alcohols undergo elimination reactions, we'll hear this commonly referred to as a dehydration of an alcohol. It's just another jargon that we have in organic chemistry that I want to make sure you're aware of. Okay, so from there, right, now the next thing that we need to take a look at is elimination reactions of sulfonate esters. So for elimination reactions of sulfonate esters, right, again, this is going to be for our benzylic, allylic, secondary, and tertiary sulfonate esters. And we're going to go ahead and draw a generic example here. So I'm going to have here a, once again, tertiary sulfonate ester. And because we know that this is some sort of a that this is going to be an E1 process, we know a carbocation has to form. The first step is going to be, right, dissociation of that leaving group to generate our carbocation. Remember, sulfonate esters are pre-activated. That is going to be a good leaving group. It's going to want to fall off. We're going to be left with our carbocation. Here I have a tertiary carbocation, so I'm not going to have to worry about rearrangements. Again, I'm using relatively simple examples to show the mechanism, to show the process by which these reaction occurs. There is, again, a lot of complexity, as we mentioned at the beginning. We got to be on the lookout for potential substitution side reactions. Luckily, our leaving group here, right, in our first 2 examples are both weak bases and relatively poor nucleophiles. Right, so now here's our leaving group. And what's nice about this case is we can use an extremely mild base. The conjugate base of our, this conjugate base that we have here, or this base from our leaving group, it's a weak base, but there are even weaker bases that we can use to do an elimination in this case. And one of those weaker bases is sodium bicarbonate. Right? Here's a full Lewis structure of sodium bicarbonate for you. And now here, sodium bicarbonate can easily deprotonate, right, our carbocation to generate our alkene. And here now our product, once again, I have picked to make a Tri-substituted alkene, nice and stable. If we look at all the products we make, right? Bicarbonate, deprotonated our carbocation, that forms carbonic acid. Right? Carbonic acid spontaneously decomposes to form water and CO2. I'm not going to go through that mechanism, but we also, right, preserve charge throughout this process, in that sodium now becomes our cation to balance out the anion generated from leaving group dissociation. All right, so here we go, E1 reactions of sulfonate esters, right? Just like in our first example, E1 reactions of alcohols, dehydration of alcohols, we see that the first step is formation of the carbocation. Second step, deprotonation of that carbocation intermediate to generate the most stable alkene we can, right? I have strategically selected my example to generate a tri-substituted alkene. We have our leaving group, weak base, poor nucleophile, so we're not going to get an SN2 side reaction. All right, and again, as with all things, most substituted is favored, and E is favored over Z in that most substituted alkene if isomers are possible. All right, so the last electrophile that we need to look at for E1 reactions or E1 eliminations is going to be alkyl halides. All right, so while alkyl halides can participate in E1 reactions, they can undergo an E1 elimination, they're really by far the worst electrophile we can think of to use in an E1 elimination. And we're going to take a look at why alkyl halides are just so terrible for this here in a moment. All right, or actually right now. So let's take a look at a tertiary alkyl halide. So get my pen working. So get a different pen. We'll start off here with a tertiary alkyl halide. And we'll put in some beta hydrogens. And we know that the first step in an E1 elimination is going to be dissociation, formation of that carbocation. And remembering back to our SN1 chemistry, we know that this process, right, is favorable in polar protic solvents, right, that helps to stabilize both the carbocation through ion dipole interactions. It also helps to sequester the leaving group once it's dissociated through hydrogen bonding interactions. And so what I'm going to do here right now is I'm going to use water as my solvent. So first thing that happens, our bromide dissociates to generate our carbocation. So here now we have our carbocation. And we've got our bromide anion leaving group. And I'm going to just draw in here for a moment water, which is our solvent. Now, we have two weak bases. One is a pretty good nucleophile. One is a moderate nucleophile. It's not too bad. Water is a decent nucleophile. And what we see here is that water is actually going to be, because water, most of our solvent molecules are sequestering the bromide, and because water is also interacting, right, with our carbocation to help stabilize it here in this intermediate, what we're going to see is that water, these ion dipole interactions, can go so far as to have water serve as either a nucleophile or a base towards our carbocation. And so if it serves as a nucleophile, what we're going to see is that we can have a lone pair on oxygen attack into that carbocation to generate a new bond. We're going to call that our nucleophilic pathway, right? And our other option is to have water deprotonate to generate our alkene. We're going to call that our basic pathway. And so the product of our basic pathway is the alkene that we're hoping to form. So here now is the product of our basic pathway, or the products, right? We're going to end up with H3O plus and Br minus. So this is from our basic path. And the products from our nucleophilic pathway, right? Here we did not deprotonate and generate our alkene. Instead, we added an OH to it. So here is the product, the initial product, oxonium from our basic pathway. A second molecule of water can come along. Deprotonate that oxonium. And I'm really hurting for new markers. Right? The products of our nucleophilic pathway result in a new alcohol. A new tertiary alcohol. So let's go back, fill in some lone pairs here. Right? And so this is from our nucleophilic pathway. Now, chemists that came along before you or I have run these reactions to see what occurs under these types of conditions, and we find that our basic pathway leads to about 65% of the product that's formed, where our nucleophilic pathway leads to about 35% of the product that's formed. This is not really a very good result for us as organic chemists, right? This is very, very unfortunate. We see that SN1 competes very, very heavily with E1, right? And so this is what we would consider a very poorly selective reaction. We don't have a lot of good control here, right? And we're not able to make enough of the product we desire under these conditions for it to be worthwhile for us to use, right, these alkyl bromide or alkyl halide type electrophiles as a starting material in an E1 reaction. So while it is possible, the product mixtures are messy in that we have a lot of SN1 product that we don't want, right? We're wasting material by doing so, especially if we're trying to form the alkene and the alkene alone. Using an alkyl bromide, using an alkyl halide in an E1 reaction, bad decision. So we try to avoid that as much as possible, and instead we rely on alcohols under acidic conditions for dehydration, E1 dehydration, or we'll use sulfonate esters, right? Again, under E1 conditions, we can get very nice yields of the alkenes that we are desiring in those cases. So a final note, right? In all E1 situations, it is possible for SN1 to compete, right? I haven't shown it for alcohols and for sulfonate esters. I've only shown it for alkyl halides. But SN1 does compete, right, for alcohols and sulfonate esters. It competes with E1. It happens. Not as bad as alkyl halides, but still enough that you need to be aware of it. The way that we get around that when we're trying to do an elimination on an alcohol or on a sulfonate ester, right? The way that we can reduce that SN1 process to being practically negligible, right? We don't even consider it really being something that goes on, is by applying heat to our reaction, okay? So when you see heat in a situation that could go either E1 or SN1, right? When we have those conditions that it's possible, it's likely to be E1, but it's possible to be SN1. If you see heat there, that automatically should tell you elimination would dominate, right? So if you see a delta over near a reaction arrow, or you see a reaction arrow and it's got heat anywhere near it, this should be your signal for elimination with no SN1, Okay, so that's going to be my last comment on this, right? Alcohols are good under acidic conditions. Sulfonate esters are good under E1 type conditions. Alkyl bromides are always terrible for E1 eliminations. And then whenever you see a delta or heat, delta means heat, it's just shorthand, right? So delta, these two things mean the same thing. It means we're heating this reaction, and that always should clue you in that elimination is going to happen without any SN1 that you really need to worry about. But even if you see heat, alkyl bromides still give you enough SN1 that you have to care. This is why alkyl bromides are terrible for E1 reactions. All right, so that's the video lecture for topic 17. As always, if you have questions, bring them to office hours, conference, or lecture. And hope you guys all have a great fall break, and I'll see you October 23rd. Thank you very much.